Well, when Thomson first did his experiment where he discovered the electron is all he knew about. He didn't know about, Rutherford, right. Rutherford discovered that there was a heavy positive core with the electrons around it. So he discovered really the structure of the atom. But at first, all he knew about was the positive charges. They didn't know that it was a neutral particle, the neutron. That was actually not discovered until about 1930. So it was 20 years after Rutherford. Okay, now I promised to tell you a little bit about nuclear bombs today. I don't want to spend a lot of time on this because I have something else even more important to talk about on our last day here. But I did want to give you an indication of the kind of energy that can be released in nuclear reactions as opposed to chemical reactions. I mean, in the kind of chemical reactions that we've studied, what you're doing is just combining whole atoms, but you're not messing with the structure of the atom. The nuclear reactions, you're actually changing the nucleus itself. And those kinds of reactions will come in two varieties, actually. We'll see in a minute. You can take a big nucleus, a big heavy nucleus like uranium, and break it apart. Or you can take very light nuclei and get them to fuse together. And that's called fusion. This is called fission, okay, breaking apart the nucleus. And this was the first thing that physicists discovered, the first new kind of nuclear reaction that was discovered. And physicists actually weren't looking for it. What they were trying to do, they had the idea of hitting this, the heaviest nucleus they knew about, uranium, with particles to try and make even heavier elements, try to make a heavier nuclei. And when they carried out that experiment, they found that not only was there a lot of heat released, but then they found trace elements of barium, which is you should have this in your notes from last time. That's barium, and the other one is krypton. These are the two elements that uranium breaks into when you break the nucleus apart. But now remember, when I finished last time by telling you about this particular reaction, which was the first nuclear reaction discovered by physicists. Well, when you break the uranium nuclei apart, it breaks into these two other elements, but then it sends out 3 neutrons. Well, it only took 1 neutron to break the uranium nucleus apart. Now, obviously, if these 3 neutrons just fly off into space, then that's the end of it. But what if you have not just 1 uranium atom here, but you have a whole big bunch of them, a whole big ball of uranium. And you get one of these uranium atoms to break apart like this. Well, it sends out these 3 neutrons. Each one of those 3 neutrons can hit another uranium nucleus. It's surrounded by other uranium nuclei. And it'll cause up to 3 more of these atoms to break apart. Each one of those sends out 3 neutrons that can cause 3 more nuclei to break apart. So you get I mean, very quickly. I mean, these neutrons are sent out at high speed, and the other uranium nuclei are very close by. So in a split second, you can get billions, trillions, quadrillions of uranium nuclei breaking apart, all releasing an enormous amount of energy. You know, I told you every single one of these reactions is, what was the number, 6 or 7 million times as energetic as the chemical reaction that's going on in dynamite. So you can see there's the possibility of a very, very large release of energy very quickly. Yeah.
What happens to the electrons that are like going around the nuclei that got broken up?
Oh, well, they just end up around these two nuclei. I mean, split up. So 36 of them would be around the krypton, and 56 of them would be around the barium. Because if you have 56 positive charges, it's going to attract 56 negative charges in order to stay neutral. So you have the possibility of a chain reaction here. Now, it turns out that this kind of chain reaction will only take place if you have enough uranium. In other words, there has to be a good chance that one of these neutrons will actually hit another nucleus. If you don't have enough uranium, then the chances are that these neutrons are just going to escape without hitting another nucleus. But at a certain point where you have enough, you'll get this chain reaction. So once physicists understood that, they realized, aha, we can make a bomb. And we can even control when it explodes. Because let's say we take two small pieces of uranium, okay, and both of them are small enough so that most of the neutrons typically escape, and they don't cause a chain reaction. But when you put them together, when you put the two pieces together, then you have enough uranium so that the chances are that these neutrons that are released will hit other nuclei, and you get the explosion. So that is, in effect, what a nuclear bomb is. Let me just... I mean, basically, let me give you just a simplified schematic of a bomb. If you have, say, you have a tube here, and you have a piece of uranium here, and let's say you have another piece of uranium here. Both of these pieces are sized such that they can't undergo a chain reaction. The neutrons, for the most part, are escaping before they hit another nucleus. But all you have to do is put them together, and you have a mass of uranium that's beyond that critical point that will undergo a chain reaction. So what they do in a nuclear bomb is you have some high explosive here. So let's say you have a charge of dynamite here that sends that piece of uranium into the core of this other piece of uranium. I mean, actual nuclear bombs are designed a little bit differently than this simplified one that I'm showing you here. But the idea is suddenly you have this what's called the supercritical mass of uranium that undergoes this explosive chain reaction with every single nuclei that's broken apart, releasing this 6 or 7 million times as much as the chemical reaction in dynamite, and all of these nuclei doing that all together. And you get a really big boom out of it. Now, it was an amazing feat to do this in just a few years. Physicists understood enough of the nuclear physics involved to see the possibility in the 1930s. And by 1945, the United States had the first bombs, which we used to win the war against Japan and save probably hundreds of thousands of American soldiers' lives. So that was an amazingly fast technological development. Now, you might ask, why should it even be so hard? I mean, if all you have to do is dig up a bunch of uranium, and there are uranium deposits. There's some big ones up in Canada and so on. Why? What's the big deal? All you have to do is dig up some uranium. And in fact, the question that comes up at this point, after what I've just told you so far, is why don't the uranium deposits themselves spontaneously explode? I mean, you got a whole bunch of uranium in some mountain in Canada. Why doesn't the whole mountain just go up in the biggest nuclear explosion in history? Sure.
Because you don't have just neutrons flying around by themselves.
Well, no, I haven't told you enough for you to figure it out yet. Based on what I've told you so far, the uranium mines should explode. The reason they don't is because uranium comes in two varieties, it turns out. The kind of uranium that I've told you about so far is the atomic weight of it was 235. It had 92 protons and 143 neutrons. Well, it turns out uranium comes in another variety. Now, what makes it uranium is that it has those 92 protons. But most of the uranium that exists naturally doesn't have the 143 neutrons that I told you about. It has 146 instead. Okay, so two types of uranium. There's U-235 and U-238. Turns out that 99% of uranium, or more than 99%, is 238. Less than 1% is this kind that actually breaks apart, the 235. Furthermore, 238 is good at absorbing neutrons. So it's like in natural uranium, there is this inbuilt mechanism that prevents chain reactions. These guys might occasionally break apart, but the neutrons they send out are just absorbed by these guys. They don't cause further chain reactions. Nick?
Wasn't there a bomb made with 238 uranium?
No, you can't make a bomb with 238. You can make it with uranium-235, or you can make it with another element called plutonium. But 238 is pretty harmless. It's not even that radioactive. It takes a very, very long time for 238 to even decay. Daniel?
Are there major groups groups of 235? I mean, that today, that what we know, what we find of it, are they in major groups or are they just scattered along?
No, when you find uranium in nature, it's always, over 99% to 238. So you're,
Find the 235.
huh?
So I said, so where in the world would you most often find the 235?
Oh, you can't find it. That's the problem. You have to make it. You have to take ordinary uranium that is 99%. I mean, if you want to use uranium for nuclear fission to release energy, you have to go out and get ordinary uranium, which is more than 99% 238, harmless stuff, and somehow separate the 235 out of it. And that is why everybody doesn't have their own nuclear bomb. Because if 235 just existed in nature, it would be trivial to make a nuclear bomb. The tricky part, and the reason why all these third world countries that don't have a lot of technology, that we don't want them to have nuclear bombs, the reason they don't have nuclear bombs is because they can't do this. They have a really hard time getting the small amount of 235 that exists in ordinary uranium. And well, I mean, I won't go into any detail telling you about how that's done. It turns out you can use this small mass difference between these two different varieties of uranium in several different ways to separate the two types and get the pure 235. But it's a very difficult process. That was the major stumbling block to building a nuclear bomb, and it took a lot of advanced technology in the United States in order to do that. Okay. Now, I mentioned that there. Oh, by the way, so I should say one more thing about this. The uranium that is used in nuclear power plants is mostly 238 still. So people that have the misconception that if some operator did something wrong at a nuclear power plant, the nuclear power plant could explode with a nuclear explosion or something. That's just nonsense. It's not even physically possible. It doesn't matter what the operator does. And this is the physical reason for it, because it's mostly 238. It's not pure 235 like you find in nuclear bombs. Okay. Now, that's all I want to say about nuclear fission. Now, I wanted to mention one thing about the other type of nuclear reaction, which is fusion, where very light atoms can actually bind together and release an enormous amount of energy by doing that. Turns out this is a really, really important reaction. It is, there was a big mystery in physics when physicists got to the point where they realized how much energy the sun was putting out. That the surface temperature of the sun was 6,000 degrees, or if we use Fahrenheit scale, almost 10,000 degrees. So here we got this 10,000 degree fireball putting out this incredible amount of energy. And then physicists figured out how old the sun was. It's billions of years old. So this is no ordinary fire. This is a fire that puts out this amount of energy for billions of years. I mean, what could possibly fuel such a thing? I mean, you would think if you had an explosion of this magnitude that it would burn itself out, in a matter of days or something. But it just goes on and on and on, billion years after billion years. So what could possibly fuel such a process? I mean, physicists in the, at the turn of the century, 1900, physicists had no clue as to any physical process that could possibly put out that amount of energy. And it turns out it's nuclear fusion. What's happening in the sun is hydrogen is turning into helium. Hydrogen atoms are coming together and forming helium atoms. And there's an enormous energy release when they do that. Even bigger than the energy release from this, from the fission process I just told you about. Yes?
When you showed us like the hydrogen and helium,
Yeah.
Helium had 2 neutrons, but there aren't any neutrons in hydrogen, so how'd they get?
Yeah, that's kind of tricky. It turns out that protons can turn into neutrons in certain, so they can, 2 protons can smack together. And once they come together, can kick out an electron, and they become a proton and a neutron. It's a complicated process. So what you have then is a hydrogen atom, a normal hydrogen atom, but with a neutron added. Okay? And then 2 of those come together, and you've got a helium atom. Okay, so that's what's going on in the sun. Hydrogen is being made into helium, and at an unbelievable rate. Over 650 million tons of hydrogen is converted to helium every second in the sun.
Where is all that hydrogen coming from?
From the sun itself. The sun starts out, the sun starts out basically a ball of hydrogen. And then it gets turned into helium as the years go by. Now eventually it will burn up its hydrogen, or most of it, and it will start cooling off, and then various things happen and so on. But we don't have to worry about that. It's not happening next week, or it'll be going for a long, long time. Right now, our sun is still 3/4 hydrogen and 1/4 helium. But it is, over 650 million tons of hydrogen are becoming helium every second. And that is what's creating this huge fireball that makes our lives possible. It is a huge nuclear fusion explosion. That's what the sun is. And it, like I say, it's been going on for billions of years. Now it takes incredible temperatures to get these hydrogen nuclei to come together and form helium nuclei. So it turns out, well, in the core of the sun, there are the temperatures that are required. It's if I give the number in Fahrenheit, the core temperature of the sun, the temperature at the center of the sun, is about 27 million degrees. So that's really hot. So this 6,000 or 10,000 degrees that we have on the surface of the sun, that's nothing compared to the temperature that you have in the middle of the sun. And that is what makes this whole nuclear fusion reaction possible that these protons in the hydrogens are so energetic that they can overcome their electrical repulsion and just smash into each other and stick together. Okay, so nuclear explosions are a good thing. You know, we're alive because of a huge nuclear explosion. So keep that in mind, despite any propaganda you might hear to the contrary. Okay. Now, I want to get started on my last, final topic for this course. And what I've decided to do in order to sum up everything we've done in the last 2 years is give you Harriman's top 10 list. Great discoveries in the history of physics. Now, I'm restricting myself to physics here because I found that if I included chemistry, I could only get it down to 12. And Harriman's top 12 just didn't have the same ring to it as Harriman's top 10. So we're just going to do physics. So now the other thing is I'm not going to do this quite like David Letterman, who works up to the very best one that he saves as number one, and he saves toward the end. We would have to skip around in history if I tried to do that, and it turns out I think it's impossible to do anyway. Because in the history of physics, we've seen the logic of it, and there's a connection between these 10. Every one of these 10 relies on the previous one. I mean, there's a starting point that I'm going to tell you about in a minute. And then you couldn't have number 2 unless you'd already had number 1. You couldn't have number 3 unless you'd had, so I mean, we'll see the logic of this. So doing them out of chronological order wouldn't make any sense. So I have to follow the chronology here. So where do you start? Identifying the greatest discoveries in the history of physics. Daniel's got an idea.
It has to be somewhere with the battery. The battery has to come into all the stuff. Now, I don't know if you want to.
Battery, okay, but that's pretty late. What year was the battery discovered?
Alessandro Volta, 1700.
Evan?
You want to know when the battery was?
Battery was 1800. A lot has happened by 1800. Okay, so you skipped a lot of stuff, but hang on to that idea and see whether the battery makes my list. It's a good suggestion. Troy, do you have? Nobody's going to get my starting point, I don't think. I'd be surprised. I think my starting point would be a surprise for you. Neat. You made me a liar. Thales. And I think the essence of Thales' discovery was that he discovered natural science. Remember, Thales, when did Thales live, by the way?
600 BC.
Yes. Now, Thales said everything is water. Now, it turns out that's wrong. But there is nevertheless, I would point to at least 2 things about it that are essentially right. First, notice Thales doesn't say everything is the will of the gods, which is what people before Thales said. Remember, we started this course 2 years ago where I described a tribe in Africa that believed in the world was created by the 9 Woots, and these gods of theirs, and they associated a god with every aspect of nature that they saw around them, and it was the will of the Woot, that that was the explanation for why things acted the way they did. Now, before science could ever get off the ground, people had to reject that whole entire attitude. People had to focus on the physical world and say, no, things have a certain nature, and that's why they act the way they do. And that is what Thales did. He looked at the world and he saw a physical world that behaved the way it did because of what it was, the properties that it had. And he didn't have to invoke any gods. So that is absolutely crucial. That is what lies behind this word natural here in his discovery of natural science. Now, I think the other thing that Thales did, hold off just a moment. Try. The other thing Thales did is contained in this word science. Even if you take the natural view and you say, okay, the physical world, we don't need to invoke gods and the supernatural in order to understand the physical world. But you look around you and you see just a million different things. There's apples and there's lemons and there's flowers and there's rocks and there's wood and there's just a million different kinds of stuff, and everything is just its own particular stuff, and it behaves in its own particular way, and that's the end of the story. Well, if you take that view, that is the end of the story. There's no science. Science, we've seen, scientists seek to discover fundamental truths of nature that make intelligible all those particular facts. Okay, where you can cite a basic truth about the world that then explains a million other things. And that's the essence of science, coming up with these broad generalizations that make the world intelligible. Otherwise, it's a chaos that you can't even hold in mind, and you can't get anywhere. So that is what Thales was aiming at here. He was aiming at understanding some basic underlying truth that would make everything else intelligible. And even though the specific truth that he latched onto is not a truth, it's wrong, it contained the right goal of science. And you think about it, what do we say today? We don't say everything is water, but we say something like this. We say everything is electrons, protons, and neutrons. That's not a much longer statement, and it's pretty close to being true. So that is Thales rejected the supernatural, recognized the autonomy of the physical world, and introduced this broad view where you look for fundamental truths. Without that, science can't get off the ground. Okay, so he has to be number one. Now, who's number two? Any guesses?
Gilbert?
You're still jumping ahead. When was Gilbert? He was 1600. Now, a lot happens. I'll give you a hint. Respect the Greeks. Yes?
Aristotle.
Aristotle. No, Aristotle, as great as he was, he was primarily a philosopher and not a scientist. I'm sticking with physics itself here. And Aristotle made unbelievably, I mean, I shouldn't say unbelievably, but he made outstanding contributions to philosophy and all the knowledge discovered after him. But he didn't make any specific great discoveries in physics. It's an astronomer that I have in mind. Aristarchus. And the specific discovery that I think was so crucially important was the figuring out the size and the distance to the moon. Oh. Now, if you, 35 years ago, men landed on the moon for the first time. And I think everybody recognized what a huge step that was, that human beings then had the power to actually leave this planet and land on one of these objects that people had been staring at in the sky for tens of thousands of years and thinking were completely out of reach. That was just 35 years ago. But way back around 280 BC, Aristarchus, in effect, made the first trip to the moon. I mean, it was a cognitive step, not a physical step. But people had just looked up at these objects we see in the sky, thinking that the nature of those objects and how far away they were was just completely unknowable. And Aristarchus broke down that barrier by employing careful observation and mathematics. Right? And that combination enabled him to prove that the moon was about 30% the diameter of the moon was about 30% that of the Earth, and its distance was about 240,000 miles away. Yeah.
Didn't he also decide that since he get the right answer size of the sun, but since he thought that it was bigger?
Yeah, exactly. I mean, I chose the moon just because he got the moon. He actually got the moon right. His numbers were right. The sun, he figured out. He gave an estimate of how far away it was, which was actually much too low. But nevertheless, that was breaking down a barrier too, because he was the first to prove, even though his estimate was wrong, he did prove that the sun was much, much bigger than the Earth, which shocked people at the time. They assumed the Earth was the biggest body in the universe and the center of the universe. And everything all these little objects just revolved around it. That was their worldview. So for Aristarchus to prove that the sun was much, much bigger than the Earth and actually show with indisputable calculations what the size of the moon was and how far away it was, that was just an enormous step. Like I said, it broke down a barrier and gave people the idea that man really can understand the universe. Okay, let me start at least on number 3. I don't think I have time to finish number 3. There's only a few minutes left. Well, I'm still even on number 3, I'm not going to make it out of ancient Greece yet. I think Greece deserves 3 out of the 10. Now, can you guess who? Sorry.
Either Aristophanes or one of the son. I can't remember his name, but I think he lived in Syracuse.
Yeah, that guy, the Syracuse guy, is the one I picked. Archimedes. Now, why? Why Archimedes? Yes.
He made like a lot of advances with mechanics and.
Well, he did. He did, and that is part of why he's important. But I would say he was the real discoverer of mathematical physics, of the application of mathematics to the physical world. And he even showed some of the remarkable ways in which such knowledge can be applied. But let's see, is that? Yeah, so you can credit him with the discovery of the subject of mathematical physics. Now remember, we covered 2 main discoveries of Archimedes. There was a law of floating bodies, the principle of buoyancy, and that a body will always displace, a floating body will always displace an equal amount of water. And then we discussed his law of levers, the fact that how you could balance 2 different weights on a lever, and as long as the ratio of the weights was the inverse of the ratios of the distance from the lever, that you would get balance. Now, those are exact mathematical laws. See, that's the key. Now, they aren't fundamental truths about the physical world. They don't compare in that sense with many of the other laws that we've talked about since, laws of electromagnetism or the law of gravitation. These are, the law of levers just applies to levers. The law of floating bodies just applies to floating bodies. So they're narrow truths of physics in that sense. But still, I think you can see he's the first, and he opened up the door to all of the mathematical laws that we've discussed since, because he discovered the first ones. He showed, no, you can take mathematics and come up with mathematical laws that are exactly true of physical bodies in the physical world. That mathematics is the key to understanding the physical world, and you can capture exact truths about that world in the form of mathematical equations. And without that, all of physics since Archimedes wouldn't have been possible. So these are the 3 from ancient Greece that made the whole era, the modern era of science, possible. Nee.
What are his dates?
Oh, I think, say around, well, if you want to, I would say that these discoveries put them around 240 BC. Archimedes' actual dates are 287 to 212. Okay, I will continue the list this afternoon, but there's 7 more coming, and with the kind of knowledge you have after this 2-year course, you should be able to rattle them off the top of your head and guess